in the geometry optics, and then our topic for this week is going to be image formation. And then I know that many of you actually struggle to understand the sign conventions, and also apply the equations to find the image, the image location, as well as the nature of the images. I hope I can clarify those doubts, okay, in this summary lecture. All right. So what we are in this image formation by lens centimeters, and then these are the topics, okay, which are aligned to your LAMS videos. So we will start with this definition of the image, and then sign conventions, and then we will look into the image formation by mirror, lens, and the reflection. And then we will also discuss about short-sighted and the far-sighted, and then finally the true range system. All right. So let me start with this. So real and then virtual images. Well, in this diagram, this vertical line represents a mirror. So this is a mirror, okay? And then we have the object, which is represented by this upright black arrow. And then your object can be a light source, like the mobile phone torch or a laser or whatever, okay? Or any object that can scatter light. Those objects can, okay, so let's say, well, a laser torch shine on this mirror, then what happened? From our daily life, we know what happened, yeah? The light will be reflected, all right? Therefore, when it comes to these sign conventions, we will always trace the real rays, okay? So let me repeat this again. When it comes to these sign conventions, we will always trace the real rays, okay, the physical ray, all right? Then, because this torch light is reflected by this mirror, we have the real rays only in front of the mirror, all right? And then behind the mirror, there's nothing, all right? So behind the mirror, there's no actual physical rays at all. Behind the mirror, it's just darkness. Makes sense, yeah? Now, I will stop sharing. All right, please look at me. All right, so how can I change my side? Oh, never mind. Well, so please look at me. Let me start with this lens. All right, so this is a lens, and this is a torch. All right, so this torch is the object to the lens, and then the object, the light, the real ray actually pass through the lens. In other words, we have the real ray or the physical ray in front of this lens because we have the torch light, and then even behind the lens, you can see this real rays. So we have a real ray in front of the lens as well as behind the lens. All right. Now, let me show you this mirror. So now this is our mirror, and then again I have the torch. Yeah. Now, when the torch shine on the mirror, then what happened? Let me see. I think this is the best angle. Yeah, this is the best angle. So what happened? The light is reflected by the mirror, isn't it? So the light is reflected by the mirror. In other words, behind the mirror, you cannot see light at all. So behind the mirror, there is no physical rays, all right? So any image formed behind the mirror must be a virtual image because it's must be formed by the virtual rays, all right? Now, please have a look at this mirror, all right? So, well, you can see that the light is reflected by the mirror, but inside the mirror, you can actually see an image of this torch. So inside the mirror, we have the image of this torch. In other words, the image is formed behind the mirror. And then this formed image must be virtual image because behind the mirror there is no physical rays. Okay, so all the definitions of real ray and then virtual rays. Well, all the definitions of the virtual image and the real image, they will follow or determined by the presence of the real ray. All right. Now I will go back to slide. Okay. So here again, this is our torch, and then torch is imaged behind the mirror, and then what would be this image? This image must be virtual image because behind the mirror there is absolutely nothing. All right. Now, before that, I also want to define two more definitions. So here, the distance between the object to the mirror, the optical element, is P. Okay, so now we denote this distance as P. And then the distance between the image and the mirror is going to be denoted as Q. All right, so this is standard in our textbook, okay, P and the Q. I know that some other textbook use as a U and the V instead, but well, as long as you understand the definition of all those symbols, that should be fine, okay? But in our context, in our textbook, we use P for the distance of the object and then Q for the distance of the image. Now, in this case, I'm going to define that P is positive according to the sign convention. And then Q is negative according to the sign convention. Why? Because P is measured following this real ray, and then Q is measured by the virtual rays. So as long as you follow the real ray, then all the signs are positive. And if you follow the virtual rays, then the signs are going to be negative. Okay, that's the fundamental of the sign conventions. All right. Now, well, let me repeat that sign convention again. Here we are given this flat mirror, and then the rays travel left to the right. Okay, left to the right. In this case, P, okay, on object in front of the mirror is going to positive because it measured, okay, or its distance is defined within this real ray region, and the image from the behind the mirror is going to be the virtual image, and then its measured distance of Q is going to be the negative value. All right. And for the spherical mirror, where we also define, this is a curved mirror. Okay, this is a part of the sphere, and then we can define the center of this curvature, and distance between the center of curvature and the mirror is measured R. All right, and with that, we have a further discussion on these sign conventions. But before that, I want to draw some diagram. All right, so let me draw some diagram. Okay. So I will start with this drawing a horizontal line, which is the principal axis, okay? And then let me draw this curve. And then our object, my object is standing on this side, and then my image is generated behind the mirror as this. All right. So we have the object. This is the object, and then this is image. And then we just learned that the distance from the object to this mirror is P. Okay, and then the distance from the image to the mirror is Q. And then according to the sign convention, this P must be positive value. So I will say this is a positive value. And then Q must be negative value because this object, this is a torch. The torch shines this mirror from left to the right. All right, so this is positive and this is negative. Now,
Yeah, sorry, Prof, your image is upside down.
Please have a look at this diagram. In this diagram, the light flow from left to the right, yeah, from left to the right, and then we have the image, so object and then image. Now I'm going to do this. I'm going to rotate it like this. Then what happened? The light flow from right to the left. All right. In this case, will this P still positive or P must be negative? What would be the sign of the P? Now the light travel from right to the left, and this P is measured here. Okay, so positive or negative? The correct answer is this P is positive. Why? Because this P is measured within this real ray. Okay, so this P actually represent this real ray direction, isn't it? Therefore, this P is positive. So you don't need to worry about this left to the right, right to the left. What you need to focus, what you need to look into, what you need to check out is that the P or the Q, whether they are measured following the real value or real ray or the virtual ray. Okay, as long as your P is measured following the real ray, then it's going to be positive value. All right. Now I will use my notepad to continue my diagram. Just 1 second. Okay. Now I'm going to draw the same diagram here, starting with this horizontal line, and then I have this concave mirror. We have an object, and then we have an image. All right. Now, this light travel from left to the right. This is our convention. Okay, so the light travel from the right to the left or left to the right. It can happen in any way, okay? Well, as long as it depends on where you actually put your object. But for the in the sign conventions, we assume that the light travel left to the right. That's why this curved surface is called concave. This is called concave, yeah, because the light travel from the left to the right. So this surface. This curvature is concave with respect to this light direction. If the light travel from right to the left, then this curvature must called convex. All right. So here, where we have only because in our sign convention, the light travel left to the right. Therefore, this is called the concave mirror. Now I'm going to define. Let me remove this object. I'm going to define the center of the curvature, and this center of the curvature is located at the distance r, which is the radius of curvature. Now, this radius curvature must be positive or negative. This must be positive value. Why? Because in front of the mirror, we have a real rays. All right. Now let me continue this. I'm going to define convex mirror like this. So in the case of the convex mirror, the center of the curvature defined behind this mirror surface, and the radius is going to be negative value because behind the mirror there is no physical ray. All right. Therefore, the radius is going to be a negative value for the convex. Now I will go back to the lecture note. Okay. Here the signs of the P and the Q you just follow whether they are measured in the following the real ray or the virtual ray. Okay, so that will define their size. However, when it comes to this radius or the focal length, well, you will just check whether the radius is still in the real region or the real ray region or the virtual ray region. So in this case, for the case of the concave, the radius is defined here. Oops. The radius is defined in front of the meter where real ray exists. Therefore, what this has the positive value. When it comes to this convex, the radius is the radius is defined behind the meter where we don't have the real ray, therefore it has a negative value. And we can also find the location of this image using the geometric optics and the derivation of this image formation equation, as well as this lateral magnification is given in the LAMS video. So please watch and study this derivation. For now, I just want to highlight that those two equations are repeatedly used for most of these image formations. So please make sure that you get familiarized with those two equations. Now, focal point and the focal length are defined when the incident parallel rays reflected through the one singular point. Then this singular point is called the focus point, and then the distance from the focal point to the surface is going to be f, which is the length of this focus. And when it comes to this curved surface, curved mirror, the focal length is half of this radius of curvature. Yeah. Therefore, in this equation, you can also equate this as 2 over r. Okay. So it's for the spectrometers. So let me repeat this again. So those two equations are applied for the other image formation equation, other image formations. So please get yourself familiarized for those two equations. Now, we can make a very interesting conclusion from this magnification. First of all, if the modulus of the magnification is larger than 1, then we know that this the image is magnified. Yeah. If this magnification is smaller than 1, then image is minified. Yeah, that's very straightforward to understand. The second conclusion is more interesting. If the magnification is positive, all right. So if this is positive, then what does this mean? Because Q is positive, then P is positive, then the Q must be negative to make positive magnification. Negative Q means this image is formed by the virtual rays. Therefore, the image is virtual image. And also, when the magnification is larger than 0, or sorry, where the magnification is a positive value, then the image and then the object, they are in the same orientation. Okay. Now, when the magnification is negative, then the image is real because the Q value must be positive to have the negative magnifications. And also the orientation of this image and the object, they are in the opposite orientation when the magnification is negative value. All right. And then I would like to introduce a few useful ways to construct the ray diagram. All right. So first, let's have a look at this blue line. An incident or parallel incident line or incident ray will be reflected through the focal point, right? And then an incident ray through this focal point will be reflected as a parallel ray, all right? So we now learn about those two rays, and then the third ray. An incident ray through this center of the focus will be reflected along the same path, right? And then finally, an incident ray to the center of this optic will reflect it symmetrically, all right? Now, with all those the useful rays, I like to give some examples for this ray diagram construction. Okay, so I'm going to use my notepad. Let me switch the screen. So, well, we will always start with this horizontal principal axis, and then I'm going to define the concave mirror, and my focal length is defined here, and then my center of the curvature is defined here, and then from our previous discussion, from the according to the sign conventions, we know that the distance, the radius of the curvature is a positive value for this concave mirror. Now I'm going to place my my object here. So object is placed between the focal point and then the mirror. All right. Now let me try to construct the ray diagram. So I will use the four the four useful rays. So first useful ray is this. So incident ray parallel to this principal axis will be reflected through the focal length. Okay, and incident ray to the center of this optics will come out symmetrically. Okay, now I'm going to introduce another ray. So incident ray through this focal length. Now I want to draw the incident ray through the focal length, but then our focal point is behind the object. But so then I might be tempted to draw like this, but this is wrong because our light travel left to the right, okay, according to the sign convention. Therefore, what I'm going to do is this. My incident ray through this focal point is going to be drawn in this way. So I'm going to connect this focal point to this object using this dashed line. And then I will extend this dashed line. I'm going to extend this the dashed line with this as an incident ray to this mirror. Then this will be reflected parallel to this principal axis. Now, the image will form when those reflected light will converge. But now in my case, all those three reflected light, they don't meet each other, they don't converge. In other words, we are not going to form real image in this case because all these the physical rays actually they diverge, yeah, so they don't meet in front of the mirror. So which means we are going to have the virtual image behind the mirror, and then I will introduce the virtual rays to define the virtual locate the virtual image. Yeah. So how are you going to introduce the virtual rays? Well, you must choose the reflected ray. Yeah. So because the image only formed after the reflection. All right. Before the light hitting the mirror, there is no image at all. So the image must be formed after the reflection. Therefore, I choose those three reflected rays and then I extend them behind the mirror. Then, well, happily we can see this converging point, and then I draw an arrow that now represents the image. Now we can see that the image is formed behind the mirror by the virtual rays. All right. Now I will draw another ray diagram for the convex mirror. So let's start with this. Sorry. Let me start with this the principal axis, and then I will draw convex mirror. My object standing here, and the center of the curvature is placed behind the mirror, and then we know that from the sign convention, this radius of curvature is negative. Okay, because behind the mirror there is no physical value, therefore this radius must be negative. Now, its focal point is placed here, which is at the half of the radius. Let me first start with this ray. Okay, so incident ray parallel to the this principal axis will reflected through this focal point. Now I want to draw line like this, but I cannot do that because behind the mirror, so all the physical rays are reflected. So behind the mirror, there is no physical rays at all. So I can't draw this line. What I have to do then, what I'm going to do is this. I'm going to introduce dashed line again. Okay, which is through this focal point, and then I will extend this dashed line like this. Then this becomes my reflected ray, okay, bounced by this the convex mirror. And I'm going to introduce another ray which will go through this the focal point. So I want to reach to this focal point, but I can't because behind the focal point, behind the mirror, there is no physical ray. So I introduce those dashed line, and then my reflection will be drawn as this. Okay. Then, well, as you can see, where those two rays, the reflections, they don't meet in front of the mirror. In other words, this convex mirror will form a virtual rays behind the mirror. So how can I define the virtual rays? Well, how can I define the virtual rays? Well, I will extend those reflected rays behind the mirror as this. Then those two reflected rays, virtual rays, meet at this point, which means this is our image formation, image location. And as we know, this image distance Q in this place is going to be negative value because this image is formed by the virtual rays. All right. I like to go back to the lecture note. All right. Well, we just practice this, yeah. So, well, with this condition, this object generates the image behind the mirror, which is virtual image. And I also show that with this convex mirror, we can generate this the virtual image behind the mirror, and then this image is minified, all right? And I like to make a conclusion about this convex mirror. This convex mirror is very often called diverging mirror because it actually reflect all the light out, yeah. So there won't be any the real image formed by this convex mirror. In general, therefore, in general, the image formed by this convex mirror is upright, virtual, and then smaller than the object. And then this kind of the mirror is also called this cosmetic mirror. The safety mirror, because it can always capture this big object into the small image and then it generates an upright image. So you can see those convex mirrors in the sharp corner in the road. And I just also show that concave mirror can also generate this virtual image, and then this virtual image is actually magnified. Okay, so when we use the convex mirror to generate the virtual image, then this virtual image is minified. But if we want enlarge the virtual image, then we are going to use the concave mirror because it can magnify the object. So it's called the makeup mirror or the shaping mirrors. Do you have any questions so far? No question? Then I will move on to the would-click questions. So I have a couple of would-click questions. So can you please scan this the QR code to start the would-click questions? I will also change the screen. So please scan this QR code, and then we will start the would-click questions. But before that, I have one question from you. So let me read the question. How to differentiate the virtual image and the real image in real life application? This is a very good question. So how can we differentiate? How do we know if this is a real image or virtual image? Well, I think I better illustrate this using the lens and the mirror again. So, well, let me stop sharing so that you can see me. So, well, this is a lens again, and then the torch is focused by the lens, okay? So the torch light is focused behind the lens somewhere here, all right? Then this image, okay, so this image, all right, focused by this lens can be projected on the screen. In other words, I place my hand here, then the image can be projected on the hand, or you can actually have the image on your hand. All right, then this is real image because the real ray actually strike my screen and then it's projected. Okay, so if you have the real image, then you can actually project the you can place the screen to capture this real image. However, when it comes to this virtual image, let's have a look at this mirror image again. What will be the best angle? All right, so right here, where you can see the image is captured inside the mirror. So behind the mirror, we have this torch image. Then I place the screen behind the mirror. Can you actually project the image? No, because there is no physical rays. Therefore, the virtual image is not going to be projected. Right? There's no physical ray actually strike this screen. Therefore, you can differentiate the virtual image and then the real image by placing a screen or paper or whatever. If the image is projected on your hand, then yeah, it is the real image. I also have one question from you. Let me read the question. The concave mirror can also produce real and minimized image when P is less than F, right? Yes, you can actually produce minimized real image, and then this minimized image formed by the concave mirror is going to be real image. It's not going to be the virtual image, all right? So your virtual image formed by concave mirror is going to be enlarged image or magnified image. All right, very good. Any other questions? No, then I will go back to the woodcraft questions. Okay, let's start. So, well, the first question. Which of the following answers best represent the type of meters? So A and B. So concave flat, flat convex. So what do you think? First of all, both actually generate the upright images. Upright images means they are virtual images, yeah? So which would be the correct answer. I am going to close the board in 5, 4, 3, 2, 1. Yeah, the correct answer is 4. All right. So on the left hand side is concave and the right hand side is the convex. I will come back to those questions later. Okay. So let me move on to the next question. With the concave mirror, when the object's distance is greater than the focal length, then the image is going to be real upright or virtual upright. So what kind of image are you going to generate with this condition? All right, I'm going to close the board in 5, 4, 3, 2, 1. All right, the correct answer is real and then inverted. Very good. So let me move on to the next question. Yeah, with a convex mirror, the image always I'm going to close the board in 5, 4, 3, 2, 1. The correct answer is 3. Yeah, butcher and then upright. Very good. Now, well, this is the next question. So I will come back to this Euclid question later, but let me go to the lecture note. Okay, so I will go through these questions again. So well, in this case, the correct answer is concave and the convex. So well, there was some confusion whether this can be flat or concave. Yeah, well, I think now, well, this is a bit confusing, but the when you look at this the image, then the image is actually magnified, enlarge the image, and then the enlarged virtual image can be formed by the concave mirror, right? Now this is the second question. So well, in this way, the object is placed behind the focal point, therefore the the object is placed behind the focal point. So when you construct the ray diagram, then you can see that the image is actually formed, all right, as inverted and also a real image. Now, you can also generate the virtual image when the object is placed between the focal length and then the mirror. And another interesting point is this: when your object is now, let's say, placed somewhere here, your object is placed in front of the center of the curvature, then your image is going to be still real image, but it's going to be, the image will appear in front of your object, all right? So when the object is placed in front of this sheet, okay, so then its image will form closer to the mirror. However, when the object is placed between the curvature and at the center of curvature and the focal point, then your image is going to form behind the object. All right. So you don't need to memorize this. Well, you can always construct a ray diagram or solve the image formation equation, but this is good to know. All right. So this is good to know. Now the next question: with a convex mirror, the image is always virtual, upright, and minimized. Okay, very good. Yeah, so this actually illustrates where regardless of this distance of the object, this is much closer to the mirror, and then this object is much further away from the mirror. But in any case, regardless of this position of the object, this convex mirror always generates a virtual, upright, and then minified image. Okay, so that's why it's called safety imaging. Now I'm going to move on to the next topic, which is the image formation by the refraction. So here, I already demonstrate using the lens, the real ray. So let's say that where we have this real ray, which is the light torch again, is and then this shaded section is a water tank, for instance. Okay, fish tank or water tank, for instance. Then the instant real ray onto this curvature is going to be imaged behind this curvature or inside this water tank, because water is transparent. So we have the real ray in front of the curvature and then behind the curvature. Therefore, our Q is going to be positive if the image is formed behind the curvature, because this Q is measured following the real rays. However, if the image is formed in front of the curvature, then this Q value is going to be smaller than 0, because all the light already gone through this this surface. Therefore, there is no light left in front of this this fish tank. Therefore, in any image formed in front of this fish tank must be virtual image. All right. So here another the sign conventions with this refractive medium And then P and Q, well, again, you will just follow these real rays, okay? But what about this radius of curvature? Where in this diagram, we have this convex surface. Therefore, our center of the curvature will be defined somewhere here, yeah? Behind this surface. And we know that inside this water tank, okay, inside this water tank, the light still, the real ray still present inside of the water tank. Therefore, this center or the radius of this curvature is measured by the real ray or following the real ray. Therefore, this is a positive ray. Okay. Now, when we are given concave surface where the center of the curvature is placed in front of this surface, then this radius of the curvature will have negative value. Okay, the sign convention states that the radius curvature is going to be negative because all the real ray already gone through this surface, all right? And then the focal length of the converging surface or diverging surface, they just follow the signs of the radius of the curvature. Then let me move on to these sign conventions in the thin lens. Again, the P and the Q, you will just follow the real rays, okay? However, when it comes to this focal length for the converging and the diverging lens, my suggestion is this. You may just want to memorize, all right? So for converging lens, the focal length is always positive. For the diverging lens, the focal length is always negative. Then what is converging lens? Converging lens means the central part of the lens is always thicker than the rest of the part. Then this is converging lens, and then this has the positive, the focal length. If the central region is thinner than the rest of the part, then this is a diverging lens whose focal length is always negative. All right. Now, well, if all those sign conventions are still very confusing, then I can suggest a backup plan, your plan B. You may want to memorize these sign conventions, and then I will tell you how to memorize these. It's not very difficult, okay? So, well, when in the LAMS video, as well as in the summary lecture, we always start with meter, yeah? We first start with the meter. So this first row represents the meter, and then the second row is well for the refractive medium. And then the first column actually have this concave the shape, and then the next column shows the convex shape. Now, the radius as well as the focal length will just follow or just copy the shape of this curvature. Therefore, this radius and the focal length is a positive value. For this convex, they will also follow this shape. Therefore, they have negative value. Now you move on to this refractive medium, then all the signs are just flipped, okay? So the signs are flipped. So for the refractive medium, now this radius and focus has a negative value, all right? And then finally for the lenses, where I like to suggest just memorize. For the converging lens, where focal length is always positive, diverging lens, focal length is always negative. And then this table is true as long as you consider the real object, all right? I have a couple of questions from the chat room, so let me read the question. For flood meters, they just give a butcher image, and the image is the same size. Yes, correct. So the flood meter will generate, will always create a butcher image, and then the image is the same size as the object. And then let me move on to the second question. How can the P in the water tank be negative? P is a positive, yeah? P is a positive. So let me go back to this diagram if it's confusion. Okay, so the light travel from left to the right according to the sign convention, all right? Therefore, this means we have this hand torch, and the hand torch shine light onto this surface. In other words, this P represents the real ray. Therefore, this must be positive value. Now, behind this surface inside the water tank, we can still define this object, but this object is going to be negative because the light travel in this direction. Therefore, this P must be negative because where if we have the torch again, then this torch must shine light into this direction. Therefore, there is no interaction between the real ray and then the surface. Okay, but with this condition, still this object can generate the image. All right. Well, how can it happen? Because we can introduce virtual object. Okay, so with the virtual object, although there is no physical interaction between the light and this element, but still you can generate the image. Okay, and then this can be yeah, I will come back to this in the one of the tutorial questions. So I will show you tutorial question later, and then we can have more discussion about this. Any other question? Yeah, I have another question. So converging lens F is positive and diverging lens F is negative. Yeah, that's right. So if it's difficult to understand, then I would suggest just memorize. For the lenses, converging lens F is always positive, diverging lens F is always negative. Any other question? No? Then I'm going to move on to the
Hello, Prof.
yeah.
Prof, I see converging surface, right? Isn't it concave?
Sorry, what was the question again? Because the voice was a bit soft.
Oh, is the converging surface concave or convex? Because I see inside the table, right? You put there concave. Is it? Yeah, converging is concave. But then at the just now, right? You put there convex, bracket convex. So which is which though?
Okay, if it was confused, then sorry about that. In our context, yeah, according to the sign convention, this shape is always concave. It's always called concave because this is concave to the with respect to this light. Okay, left to the right, then this is concave. And then this convex, this shape is always convex because of the light travel to this direction. Is it answer to your question?
Oh, I see. Okay. Thanks, bro.
All right, thanks. Any other question? All right, then I'm going to move on to the next part. Now, we have some idea about the sign conventions with this water tank, okay? And then we can also find the image location, and then we can also define the nature of the images, okay? Where based on some equation, and then that equation can be derived using this geometry optics, and where this is the final derived the equation, and then where this derivation again explained in the LAMS image, the LAMS videos, all right? So where here you can see that the N1 is the refractive index where the object is present, and the N2 is index where the index of this second medium, and the R is the radius of curvature. And then those PQR data signs will be defined by according to the sign conventions, all right? Now I have one example for this, for using this to apply this equation. So let's assume that we have this flat surface like the swimming pool. Then from our daily life, we know that this floor of this swimming pool always appear shallower. Yeah, so its apparent image appear above the actual floor. So where we can actually confirm this using by solving this equation. So the radius of the curvature. So because we consider the flat surface, therefore the radius curvature is going to infinity. Then this equation will be simplified to this, all right? And where the object, so the floor, the ground or the floor of this the swimming pool is 1 meter. Therefore, the P is 1 meter, and the index of the water is 1.33, and the index of the air is 1. And then you solve this equation. Then for the Q, then Q is found as minus 0.75 meters. So we have a negative sign, which means Q is virtual image. It should appear at the same side of the object. Therefore, you can actually draw this the image point inside this water. Okay. Now, the next topic is the thin lens equations. Again, the derivation of these thin lens the equations are given in the LAMS video, so I will just skip those. Yeah, I just want to encourage you to watch the LAMS videos for the derivations. But starting point is this equation, the equation we just derived from this the water tank. So where you can apply that equation for this curvature, and then you apply the previous equation for the opposite curvature. Then you combine those two equations, which will lead to this Lenz-Makers equation as well as thin lens equation. Okay, and then this Lenz-Makers this equation is called the Lenz-Makers equation because if you know this index of the glass, then depending on how you shape those two curvatures, you can always adjust the focal length. Okay, so that's why it's called the Lenz-Makers equation. So again, where we have a Lenz-Makers equation, thin lens equation, and then lateral magnification. And then if you have a good eye, well, you still remember that those two equations were also used for the mirror image formations. Okay, we use the same equations. And then now it's time to talk about the ray diagrams for the thin lenses. So I think it's best to show you actual construction. So I'm going to use my notepad. Just 1 second. Let me switch the screen. Okay, so let me start with the horizontal line, which is the principal axis, and then I'm going to start with this the converging lens. And this converging lens is transparent and it has two curvatures. Therefore, I can define the focal point. Okay, for this surface here, and then for the next surface here. So we have two the focal point, and then this focal point in front of the lens is called focal point of the object or object focal point, and then behind the lens, the focal point is called the image focal point. Now I'm going to put object somewhere here, all right, and then we are going to use the same useful rays. The parallel incident ray will go through the focal point, okay, and the imaging focal point, and the incident ray through the object focal point will reflect to the parallel ray. All right. Now, and then incident ray to the center of this lens will just come out as a straight line. So where those three reflected rays actually meet here, therefore I can draw an object. I draw the image and whose distance is Q, which is a positive value because this is a real image. Now, I'm going to repeat this ray construction for this case. Now, our object is placed here. All right, then let's see what we are going to end up with. I'm going to introduce the parallel incident ray, and then parallel incident ray will reflect to the focal point. Okay, so this is good. And then my next ray is going to be incident ray through the focal point. Now, while our focal point is behind the object, therefore, I cannot draw this way, yeah, because the light travel left to the right, so I can't use this backward direction. Instead, what I'm going to do is I will introduce the dashed line to connect the focal point to this object, and then I will extend this toward this lens. And this line serves as the incident ray through this focal point, which will reflect as a parallel ray. All right. Now, if you look at those two refracted rays, they don't meet, they don't converge, which means we are not going to have a real image in this case. We need to introduce virtual rays. And what kind of virtual ray are we going to how are we going to introduce the virtual rays? Well, we have to look at those two refracted rays and then extend it to the opposite direction. Then, well, clearly those two virtual rays meet at this point, and then I will then draw the arrow, which now become the virtual image. Therefore, the Q is a negative value. All right. Now I will draw some tricky one, the converging, the diverging lens. So let me start with this principal axis, and then I will draw the diverging lens, and I can define those two focal points again. But for the diverging lens, my image focal point is in front of this lens, and my object focal point is behind the lens. Okay, because well, in the converging lens, this convex surface is placed first, okay, in the left, and then followed by this diverging surface, the concave surface. Now, this diverging lens has actually the opposite the orientation, so opposite the arrangement. So concave surface is placed toward this object, and then convex is placed toward this the behind this concave mirror. Therefore, our focal length focal point arrangement also swapped. All right. Now I'm going to introduce a focal the object here. Now let me try to draw construct this ray diagram. An incident ray parallel to this lens will reflect through the focal point. Now, well, my image focal point is placed here. Therefore, what I'm going to do is I'm going to introduce a dashed line to connect this image focal point to the incident ray, and then this will reflect out as this. Now, the second useful ray, an incident ray through the focal point. Yeah, so incident ray through the focal point, but this incident ray cannot actually reach this focal point because the light must reflect it. So I will introduce the dashed line. And then this incident ray through the focal point will be refracted as a parallel. Now, clearly, those two reflected rays, they do not converge. So we are not going to have the imaging behind the lens. In other words, we should introduce the virtual rays. So I'm going to introduce virtual rays by extending those two refracted the rays. Then they actually meet at this point. Therefore, my image will form in front of the lens, and therefore my Q is negative value because this is the real this is the virtual image. All right. Now I have one question in the chat room. Let me read. When drawing the diagram, it's important that we draw it to the scale, right? All right. Yes, it's good to make all the diagram to the scale, but I know that it's not always easy to draw it to the scale. So what I usually do is I don't actually draw this ray diagram to find the actual location. What I do is I will solve this image formation equation. Yeah, you remember 1 over P plus 1 over Q equals 1 over F. I'm going to solve this equation for the Q. Then, depending on the numerical values of the P and the F, my Q can be positive value or my Q can be negative value. All right. If my Q is a positive value, then I will have the image behind the lens like this, and then I just draw the image at the calculated Q value. And then I will construct the diagram to confirm my calculation. All right, so what I'm going to do is, again, when I will first solve this image formation equation, and then I will place the determine the Q values in the diagram, and then I will construct the ray diagram using those rays to confirm my calculation. All right. I have a few more questions. Just 1 second. The next question. For the lens maker's equation, should we consider the positive and the negative sign for the R1 and the R2? If yes, how to determine the sign? Oh, this is a very good question. Yes, you need to define, you need to consider the signs of the R1 and the R2. All right. And then how we determine the sign? Well, you are going to use these sign conventions. For instance, let's have a look at this, the diverging lens. So first of all, diverging lens is composed of those two surfaces, yeah? Say surface 1 and then surface 2. So this surface 1 is a concave surface, therefore its radius curvature is negative. Where on the other hand, this S2 is a convex surface, therefore its radius curvature is positive. So you will use your sign conventions, okay, to define the signs of R1 and R2 for the lens maker's equation. Now I'm going to move on to the next question. Can repeat what are the lines to note for the diagram? All right, so well, basically there are 4 useful rays, but you do not need to draw all the 4 rays. Okay, so if you are confident, then you may just draw 2 lines, that's good enough. All right, or you may just add 1 more, so 3 rays, that's good enough. Okay, to locate the position of this image. And again, how to draw those lines? Well, I just explained to you, okay? But if you have further questions, or if you're still not sure about this the ray constructions, please remain after the session. Then we can go through this ray diagram construction again. All right. I will. Okay, so I have 1 more question. Can I ask about what are the focal point for the object and the focal point for image should be representing? And for now, I understand I should assume the focal point for the object should be on the same side as the object for the converging lens and the opposite for the diverging lens. Okay, so so your conclusion is correct. And again, those focal are determined based on your surface, the curvature of these surfaces. So this is the first surface, and then its focal point is defined here. All right, and then this is the second focal point and surface, and the focal point is defined here. And well, because we define this focal point for this convex, the surface. When we move to this converging lens, the convex surface is actually appearing here. Therefore, our focal point is on the same side of this surface. All right. Now I will move on to the next question. All right. Why the Q is negative? I think that refers to my the last the ray diagram. The Q is negative because Q is formed in front of the lens, okay, where the lens is transparent, therefore all the light already were gone through this lens. So in front of the lens, there's no light left. If any image is formed in front of the lens, they must be formed by the virtual rays. All right, therefore the Q is negative value. Can we use new Cartesian sign convention? So sorry, I'm not very sure about this Cartesian sign convention. Can you please remain after the session, and then you can explain to me, then I will answer to you. And then I have another question about the R. R be positive for S1 since it's concave. All right, so this one I will also come back to later, okay? please stay after this session. I will discuss all those. Now I think we can go back to this lecture note. So just 1 second. All right. So I just is where to show you how to construct those Lie diagrams using those 3 useful ways. And then when it comes to this diverging lens, please make sure that your the focal point definitions are swapped. Yeah, it's opposite to the converging lens. So diverging lens, converging lens. Yeah, well, this is actually where the emphasize the change of the focal point well between the converging and the diverging lens. All right. And then I just show you how to construct the ray diagram for the converging and the diverging lens. So I'm going to move on to this would-like question. So let me now change the screen. So this is our first question. So we have the converging lens, converging lens, convex lens, and then object standing between the focal point and the lens. Then what would be the resultant image? I will close the board in 5, 4, 3, 2, 1. Yeah, the correct answer is 4. Very good. Now, this is our second question. So for a concave lens at any object distance, the resulting image is so for the concave lens or diverging lens, what will be our resulting image? I will close the board in 5, 4, 3, 2, 1. The correct answer is to always butcher, upright, and reduce. All right, it's like the convex mirror. This question is a bit more demanding. Object is located 50 centimeters from a diverging lens, having a focal length of 15 centimeters. Which of the following statement is true regarding the image formed by the lens? So I give you a hint. We are considering the diverging lens. So what will be the resulting the image? All right, I'm going to close the board in 3, 2, 1. Yeah, the correct answer is 3. All right. Now, where this, I'm going to come to this question later. Okay, so let me go back to the lecture note. So first question: when the object is placed between the focal length and the lens itself, then the resultant image is going to butcher, upright, and enlarge it. Okay, you can confirm this using the image formation equation. Okay, using when you plug in those numbers, then you should be able to confirm this result. And for the concave lens, we are going to always have butcher, upright, and then reduced. Okay, so diverging lens always generate butcher, upright, reduced, as long as the object is a real object. And where the last question, we consider the diverging lens, then we are not going to, even without we're considering all those values, all those numbers, we already know that the answer is 3. So the diverging lens always form the butcher, upright, minified images. And then you can solve this equation, okay, image formation equation to determine the Q value as well as the magnification. Then the Q must be negative sign because converging a diverging lens generate the butcher image. Now, let me talk about the next topic, which is eye accommodation. So our eye is attached to the muscle. Therefore, those two curvatures can be adjusted. And then if you look at this lens diagram, lens matrix equation, then depending on the radius curvatures, your focal length can be adjusted. Therefore, our lens is considered a variable focusing lens, and our lens can focus any object between near point and the far point. The near point is typically at the 25 centimeters from the eyeball, from the lens, and then far point is at the infinity. Okay, any object between those two points can be focused or imaged by our eyes. Yeah, this is very good. But unfortunately, sometimes our vision is some degraded or deteriorated. Therefore, we need some eye correction. Yeah, so I wear my corrective lenses as well. And then nearsighted means the far point becomes shorter and is not infinity any longer. For instance, this person's the far point now unfortunately becomes 5 meters. Okay, it's like me, where I can't focus any object beyond this far point. But I want to go to the cinema and watch a movie, and then this screen is 15 meters away. So I can't focus this object. Then what I have to do? I need to wear some corrective glasses. And then the function, the role of the corrective glasses is to form an image of the object at the far point. Okay, I'm going to repeat again. The role of the corrective lens is to form an image at the far point. Okay, so with the diverging lens, the object will be imaged at the far point. Therefore, I can enjoy the movie. Now, well, for the far-sighted vision, the near point now it's not in the at the 25 centimeter anymore. It's much further away. It's like 1 meter. So therefore, when I want to read a book or to watch the YouTube in the iPad, then the iPad placed at the 30 centimeters 30 centimeters from my eyeball, this cannot be focused. This cannot be imaged. Okay, so I will just end up with the blur image. So what do I have to do? I need to wear a corrective lens, and then the function of the corrective lens is again to generate the image of this object at the near point. Okay, so when it comes to these corrective lenses questions, where the role of the lenses is to form image at the near point or the far point. All right. So, well, which image do we want to form by the corrective lenses? Well, without thinking a lot, well, we want to have the upright image, and then you can generate the upright image means this image is a virtual image. Therefore, your Q value image, the Q value, the image location, image distance is going to be negative value because of the electric image, the upright image means virtual image, therefore Q is negative. Now, this is the one of your tutorial question, and then when it states that near point of person eye is 60 centimeters to see the object at 25 centimeters, then what should be the focal length of the corrective lens? So, well, again, the function of the corrective lens is to form an image at the near point. Okay, so because we consider the near point, so let me draw some representative diagram. Object is at 25 centimeters. Okay, so where my tablet is at 25 centimeters. So this is my object, all right, P. And then let's say where my lens is here. Okay, so here to here, this is 25 centimeters. Okay, so this is 25 centimeters to 5. And my near point is at the 60 centimeters. So this is near point. What's the role of the corrective lens? So I need some corrective lens. Yeah. What's the role of the corrective lens? The role of the corrective lens is to form image of the object at the near point. Therefore, my Q is going to be defined from the lens to this near point. And then this is Q. Okay, so you are going to construct this kind of diagram to solve this near point or far point questions. Now, well, let me move on to the two lens system. I'm very sorry, but most likely I will overshoot about 10 minutes. I'm so sorry about that. But I also have one question in the chat room. So let me read the question. The near point is the point at which the image is formed, right? Yes, we want form an image at the near point with the corrective glasses. All right, very good. Now, this two-range system is going to be our last topic, so please bear with me for another 10 minutes, sorry. So well, here in this diagram, we consider two-range system, and then our object is placed here. How are we going to handle this kind of two-range system or lens mirror systems? The first step is to analyze the light flow direction. What does this mean? So this is our object, the hand torch, and then the hand torch will shine to the lens 1 and the lens 2, this system. Our light will first go through the lens 1, okay, and the lens 1 is transparent, so well, it's really just refractive, okay, and then this light, reflected light, is going to continue to this lens 2 and then reflect again. So the light flow in this two-range system is just left to the right. That's it. Okay, so our light will travel left to right. That's it. Then we will consider lens 1 and the lens 2 separately in consecutive manner. What do you mean? Well, first we will define the image formed by the lens 1, and then when you consider this lens 1, then you just discard the lens 2. Yeah, you just treat there is no lens 2. Okay, so we only consider lens 1. Now, the image formed by lens 1 is now become an object to this lens 2. Okay, and then we'll continue this the calculation or the lay diagram. Then our image formed by lens 2 is actually appearing here. Now, our final image appears in front of this lens. Therefore, this image is virtual image. All right. And then its Q value is going to be negative. And then one example is actually introduced in the last video. So please watch the video and then see whether you can actually come up, you can actually have the same answer. All right. Here, I want to highlight this section. The total magnification of this system is going to be determined by multiplying the individual magnifications. M1 is defined here, M2 defined here, defined in the second lens, and then your total magnification is simply M1 times M2. All right. Now, the total magnification is minus 0.667. So M is negative, which means the final image is inverted. Okay, so we already learned that if the magnification is negative value, then object and the image they are in the opposite directions. Yeah, and also the modulus of the M is smaller than 1, therefore the image is minified. Now I know that you are smart, and then you also want to make a conclusion. This magnification is a negative value, which means this image is real, because negative magnification means Q is positive. Okay, so you now conclude that the image, final image, must be real image, but unfortunately it's not. The nature of the image, whether it's real or the virtual, okay, this must be confirmed by your Q2 value, your final Q value. If, well, in our example, the Q value, the final Q value is minus, which means the final image is a virtual image. Okay, so final image is virtual. Okay, so from the total magnification, you can determine the orientation of this image and also the magnification of the image. However, you cannot determine, you should not determine whether it's a virtual or real image based on your total magnification. You should go back to your diagram or your calculation to confirm the sign of your final Q value. If your sign of the final Q value is negative, then it must be virtual image. If positive, then it's a real image. All right. Now, this is a tutorial question. All right. This is confusing. I understand that. I will give you a quick diagram, okay, to analyze this. All right, so bear with me. I will show you my screen, to my notepad. Right. So I'm going to draw that. I just copied the. Sorry, I will just copy the same diagram here. We have lens and then a mirror, and then object is placed here. And then the very first step to solve this kind of question is to analyze the light direction. Okay, so let's analyze the light direction. Now, when I see that the hand torch light will first reflected by the lens, and then when it strikes this mirror, then it's going to bounce back, all right? And then it will hit this lens again and then come out, and where we form the final image. So our ray flow direction is determined as this. Okay, first it will go into flow left to the right, and then after this mirror, it will flow right to the left. All right, now all the values is given. Therefore, you are going to use this equation, okay, image formation equation, to find this Q by lens by mirror, and then again by the lens to find to find the final the image. Now, if you solve this equation for the first interaction with the lens, then your image, you will see that your image will form behind this mirror. So and then this is a real image formed by the lens. Now, this image now become an object to this mirror. All right, and light flow this direction. What does that mean? This object is going to be virtual object. So when this object, the light travel left to the right. In other words, this object, let's say this object is still torch, okay, hand torch, and then this hand torch shine light to the left, to the right, okay, according to this the light flow direction. Therefore, there is no actual interaction between this object and this the mirror. In other words, this must be virtual object, which means its measured p-value is negative. All right. Now, with this, you are going to solve this equation for this mirror, and then you will find that its next image will appear here. All right. Then this image now become an object to this lens. All right. So this is our P3 object to the lens. Is this a P3 positive or negative? What do you think? This P3 should be positive or negative?
Positive, Prof?
This is going to be
Positive.
positive, because after the mirror, light is now bounced back. Therefore, the actual light flow this direction. In other words, this object represents the real rays. So the P3 must be positive. Okay, you remember when I started this the summary lecture, I show you this diagram, and what did I do? I just rotate this to reverse this light flow direction, and then you agree that this P is still positive because the light it follow the real ray direction. Okay, so I hope this give you some enhance your understanding about the sign conventions, right? Now I will move on to our last question. So consider an air pocket immersed in the water as illustrated in the diagram. The air pocket works as converging, diverging, converging mirror or diverging mirror. So I will switch to the board again. I will close the board in 5, 4, 3, 2, 1. The correct answer is diverging lens. Please don't upset. I will explain you why. So I'm going to use my notepad again to draw some diagram. Just 1 second. You are quite right. Okay, so this air pocket is drawn as this. So where the center is thicker than the rest of the part, which means this is so this is converging. Okay, so if this shape is made of glass, okay, so glass, then surely this is converging lens, Now we have the same shape, okay, the same shape, but inside this shape is air and the outside is glass. Then what would happen? Okay, I'm going to draw a diagram to convince you that this rounded air pocket actually serve as the diverging lens. So let me draw some big air pocket, and I'm going to draw incident light into this air pocket. Okay, then at the intersection point, I can draw this tangent line, okay, as an interface, and then I can also introduce the vertical line to define angle of incidence. Yeah, and where the air pocket has index 1, and then outside is water, so index 1.33. So the second medium has a lower refractive index than the first medium. Therefore, the light will refract toward water. Yeah, refract toward a higher refractivity index medium. So therefore, this will reflect into this direction with angle of the refraction, which is larger than the incident angle. And where at this intersection point, I can draw. I can draw the tangent line again that represent the interface, and then I will draw normal line. And then this is going to be the angle of incidence again to this interface. And now you see that this water has a higher refractive index. Therefore, this will reflect into the water. So the incident ray actually reflect out when the pocket, this rounded shape is made by the lower refractive index. Okay, just in case if you are still not very convinced, then I will show you some small demo. So let me stop the share. All right, so I have this resin, okay, made of the plastic, and then this resin has a higher refractive index. All right, and then on the other hand, I have this the plastic container, so it's just empty container. Okay, so this is now now this serves as an air pocket. What I'm going to do is I'm going to put this air pocket into this water cup. Okay, into the water. Now we expect that this resin will serve as a converging lens. So any light incident into this, the resin will focus or bend toward the center. Okay, bend toward the center because this is a converging lens. All right. However, with this air pocket in the water, the incident light will reflect out. Okay, because this now serves as a diverging lens according to our analysis. So let's see whether this is really true. So in order to do that, I'm going to connect my second camera. So that's 1 second. All right, I will share my second camera. Great. Now let me start with this resin. All right, and then as we dispersed, the incident light will. All right, so I'm using this the laser pointer. The incident light will reflect to the center. Okay, because this is converging lens. So the light reflect toward the center. Okay, as we expected. Now I'm going to move on to the air pocket in the water, what do you expect? The light must be reflect out. So let's see whether that happens. So I move the laser light. Then you see the light is actually reflect out. Okay, reflect out. It does not go to the center, so it's a reflect out. So we confirm that the air pocket in the water serve as a diverging lens. All right. So with that, I think this is the end of today's the summary lecture. I will see you next week. And then if you have further questions, please stay in the session. I will answer to your questions. Thank you. Bye.
Hello, Prof. Thank you, Prof.
Thank you. Bye.
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 Thank you, Prof.
감사합니다, Prof.
Bye bye.
Thank you, Prof.
Thanks. I have a few questions in the chat room, so let me go one by one. So new Cartesian sign convention for the use of the mirror equations. All the distance should be measured from the pole. The distance measured in the direction of incident light to be taken as a positive. The distance measured in the opposite direction of incident light to be taken negative. Height measured upward, yeah, is a positive, and the height measured downward is going to be negative. Let me see. The distance measured in direction of the incident light to be taken positive. The distance measured in the opposite direction of the incident light to be taken as negative. All right. For the very first sentence, the distance measured in the direction of incident light to be taken positive. I agree with that. This is true as long as we consider only the real ray, okay, real object, then this is true. And then the second statement, the distance measured in the opposite direction of the incident light to be taken as a negative. This can be also true as long as the object is a real object. Okay, but I do not know whether you, so if you are comfortable with this Cartesian sign convention, then you may want to follow this and then confirm whether those sign conventions in the textbook, okay, actually consistent with your Cartesian sign convention. Otherwise, you have to come back to these textbook sign conventions. Okay, so as the name suggests, this is the sign convention most widely accepted, all right, in many of the textbooks.
Prof has sent a link to the picture. You can see that.
Sorry?
I sent a link to the picture of what I'm talking about.
I don't quite sure. How can I receive your this?
I sent it on the chat.
All right, let me see. I actually don't see your image in the chat room.
I sent a link.
Link. Yeah. Well, so can we have some individual discussion later? Okay, because I also need to check your link. So let me first have a look at your link, and I will come back to you. The next question. The near point is a point at which image is formed. Yes, I already explained to that. And then the next question, is it possible for the image to be inverted and magnified? If so, what will be the value of m negative and more than 1? Okay, yes, it's possible that the image is inverted and magnified. And then I'm going to restrict our discussion only for these real objects. Okay, so when we are given real object, and then when the real object is imaged by the converging lens or the concave mirror, you can actually generate inverted image and then magnified. So the image is going to be real image and the magnified image. You can have that. And what would be the value of m? The magnification. So first of all, the sign of the magnification will be determined by the sign of Q and the P. And then we agree that this discussion is going to be constrained for this real object only. Therefore, the P is a positive value, all right? And the inverted image means this is the real image. Therefore, the Q is also positive. So P positive, Q positive. Therefore, your magnification will have a negative value. In other words, the object and then image are in the opposite orientation, which also agree with your assumption, yeah, inverted image. Now, yes, and then the value will be larger than 1 because it's magnified, all right? Now I will go to the other question. Why does the ray not reflect at the center like the lens? I'm not quite sure in what context you ask this question. So maybe can you ask me later about repeat this question again later. I will move on to the next question. So M is actually refractive index, or large M is actually refractive index. Sorry, well, I'm not sure why there is such confusion, but large M represent the magnification, and then yeah, small n, M for November, yeah, is the refractive index. Yeah, I think I cover. Okay, well, I have 2 more questions. Okay, referring to the last sketch you did for the air bubble, the final reflected Y is not on the other side of the normal. Oh, okay, sorry. Well, if that happened, it's my mistake. It should be on the other side of the normal. Sorry about that. It's my mistake. All right. So let me go back to the diagram. Yeah. Sorry. Yes. Where is so I will share the notepad. Just 1 second. All right. Why touch not up? Oh yeah. Just 1 second. Let me make the connection again. Okay, sorry. Okay, so my notepad is up. Yeah, sorry. Yeah, you're right. So this reflection should not appear here. This reflection should appear here. Okay, and then because the water has a higher refractive index, therefore the light will bend toward the water as this. Okay, so it still reflect out. Very good. Let me go back to the chat room. Just 1 second. Where is it?
Prof, can you hear me, Prof?
Yep.
Oh yeah. Sorry. May I ask a question on the thin lens derivation? I hope you have some time to discuss about it. Yeah.
Okay.
So for the thin lens, if you are able to go back to the note slide on the share screen, the very first part where the ray enters the first surface, I noticed the image we choose to say that it forms is a virtual image on the same side as the object. For the
Just 1 second.
yeah. Sorry, for the thin lens.
Yeah.
And
I'm going there. Just 1 second.
yeah, thank you, Prof.
This one, yeah.
Yeah, Prof. So my question is, because I'm talking about image 1, right? I really am not sure how image 1 gets shown on that side of the when the ray first enters from the left to the right. Yeah.
Well, that's a very good question. All right. So this is a starting point. You're right. You're absolutely right. The image can be formed well in front of this surface, or it can be formed behind the surface one. You're right.
Okay.
But for the sake of simplicity or the discussion, we first assume that the image is formed behind the surface, or so behind the object or in front of the surface.
Okay.
That's our very first assumption.
So my question is, if we assume it is coming behind the object, do we assume it's a virtual image? Sorry.
Right? Yeah.
Oh, okay. I see. But the rays are being refracted still, right, Prof? Just to clarify. Like as the rays come left to right, they are refracted, and we trace the virtual rays to get the image, right?
Yes.
Okay, can.
Very good. And
Okay.
then oh, it's not here. Okay, so let me see. So when you watch the video, then after this the conclusion, yeah, there is another diagram to explain what would happen if the first image formed behind the surface one.
Okay.
And then you will have the same conclusion. It
understood.
explains that you still have the same conclusion.
Okay.
All right.
Yeah.
If you still have some question, then you doubt, then you can come back to me later. Right?
Will do. Yeah. Thank you, bro.
Very good. Thanks. And then yeah, well, it seems like I have another question in the chat room. Just 1 second. Okay, I'm going to read the question. For diverging lens and then converging lens, how do you find the sign for R1 and R2? All right, so for the lens, so the thin lens, yeah, there is no R. So for the derivation, okay, to derive the Langevin equation and then thin lens equation, we consider R1 and the R2 just for the derivation. But when we want to analyze the lens itself, we don't consider the radius of the curvature for the lens. All right. Therefore, when we come to the thin lens, you don't need to worry about the R1 and R2. All right. Unless you want to use this Langevin equation. Okay, so if you want to use the Langevin equation, then yeah, obviously you must need to define the R1 and the R2. And then, well, if we are given this diverging lens, then because the light travel left to the right, yeah, therefore this convex surface serve as R1. Okay, we define R1, and then the concave surface we define R2. Okay, and then according to the sign convention, this R1 is a positive, and then R2 is negative. Okay, and then yes, diverging, and then this is converging lens, and then well, for the diverging lens, so this is a diverging lens, isn't it? So this is a diverging lens. And then again, if we assume we just follow the sign convention, so the light travels this direction, which means the light first interacts this surface, okay, with R1, and then followed by the second surface with R2. All right, so we first define R1 and the R2 based on the light flow direction. All right, now what about the sign? Well, we use the sign convention. So this is concave, therefore R1 is negative. This is the second surface is convex, therefore R2 is positive. Okay. I have another question, so let me read the question. Why does the ray refract at the surface of the air bubble, but for the thin lens, it reflects at the center of the lens instead of the surface of the, yeah. So, well, by right, I should draw the rays in the thin lens, even in the thin lens, as I did for the air bubble by right. That's the correct representation. However, as the name suggests, this is a thin lens, which means we ignore, okay, the refraction happening inside the lens because it's so thin. Okay, so refraction inside this lens is not our interest anymore because it is so thin. All right, therefore, what you need to do is you just need to understand the incident ray, for instance, goes through the focal point, and then the light through the focal point will reflect out as a parallel ray, and then light incident to the center will just come out as a straight line. All right. And any other question? No? Then I will close the session. And then I think there is a still remaining question about the Cartesian sign conventions. So when the student who asked me this question, please stay in the session, okay? But for now, I'm going to close the session. So I will stop recording and also stop sharing.